Contrary to what you'd expect from a system of planets that formed together from a rapidly rotating nebula, our solar system presents us with a series of anomalies that seem to mock the idea of a common origin. It remains quite a mystery to understand why the heck the planet's rotation axes are so differently tilted, not to mention Venus and Uranus, which actually spin backwards, with no retrograde rotation around their own axes. Keep watching if you want to try to make sense of it all. The problem of planetary rotations has been strangely ignored by astronomers, so wrote Fred Hoyle in 1978 in Cosmogony of the Solar System, complaining that until then nobody had bothered to seriously tackle the puzzle of the disparate inclinations of rotation axes in the solar system. Nearly half a century later, things haven't improved much, and the problem still bounces between very different hypotheses, to the point that this video doesn't pretend to give definitive answers, but simply to instill some healthy doubts about the explanations that are normally trotted out. The model that's currently most popular for describing the formation of the solar system is the nebular one. Trying to condense over 4 billion years of planetary evolution into a few lines, we could say that at the origin of the system, there was a cloud of gas and dust that began to collapse in on itself. It doesn't matter here to establish what triggered that process, or whether that collapse involved multiple regions of the same cloud, resulting in the birth of other stars besides the Sun. What happened is that the dust and gas of the protosolar cloud began to feel their mutual gravitational attraction more and more intensely. First inevitable consequence, the cloud began to collapse on itself. Then, thanks to the conservation of angular momentum, a physical principle whereby an object, a mass of gas or generic system in motion increases its rotation speed as it shrinks, the cloud went from spherical to more disk-like. What was taking shape was what planetologists call the protoplanetary disk, sometimes abbreviated to ProPlide, the true cradle of the planets. It's indeed within this disk that, with different rhythms due to the nature and abundance of available materials, the particular chemical-physical conditions of different regions, and the dynamic actions exerted by the planets that formed first, the formation of the Sun's family of planets gradually came about. Now, since planets, as the nebular theory maintains, come from the gas and dust of the disk aggregating in a process of hierarchical accumulation involving ever larger clumps, we should expect, given the perfect randomness of the aggregative process, that each of them would show a rotation regime that mirrors that of the disk from which it originated. In plain terms, logic would dictate that the planet's rotation axis should be roughly perpendicular to the plane of their orbit. We all know, however, that things aren't like that at all, and just a glance at the actual inclination of each planet's rotation axis leaves us facing a situation that's anything but comfortable. Mercury 0.01 degrees, Venus 167.36 degrees, Earth 23.45 degrees, Mars 25.19 degrees, Jupiter 3.13 degrees, Saturn 26.7 degrees, Uranus 97.86 degrees, Neptune 28.31 degrees. From this data, you can easily see the enormous disparity of values, with a range going from Mercury's 0.01 degrees to Venus at 177.36 degrees. In short, while the planets' orbits are almost perfectly flattened on the same plane, the situation of their rotation axis is another story. The only planets that meet our expectations are Jupiter and Mercury, although the latter's negligible mass and its position right next to the Sun make its case rather special. Nothing to object about Jupiter, though unfortunately for us, it seems we should consider it more an isolated exception than confirmation of our expectations. So it's worth trying to reason through this bizarre distribution of planetary obliquities. Hey Curious Squad, before moving on, be sure to subscribe to our channel, clicking on the notification bell, and leave us a thumbs up so you don't miss out on our daily videos. The most credited hypothesis: impacts. At this point, it makes sense to focus attention on what's widely invoked as the most logical explanation: the action of cosmic impacts. The current obliquities would be the consequence of colossal collisions that occurred during what planetologists call the late heavy bombardment period, which ended around 3.5 billion years ago. Planetary formation wasn't just the result of a gentle, slow aggregation of dust. As objects grew larger, the violence of collisions also increased. Planetologists typically distinguish three phases of aggregation. An initial phase, the least violent, in which planetesimals of about 1 kilometer form. An intermediate phase in which planetesimals grow to lunar dimensions. And a final stage, the most violent, in which aggregation results in the construction of actual planets. Numerical simulations show that in the first two phases there was likely a sort of homogenization of rotations, so that planetary embryos should have had direct rotation and practically zero obliquity. Very different was the scenario in the final stage. It was in that turbulent epoch, incidentally, that's when the formation of our moon is dated, that impacts so violent occurred as to leave a permanent mark on planetary rotation regimes. A certainly plausible explanation from a dynamic point of view and astronomically grounded, but one that has some weak points. Sure, nobody today dares doubt the violence that characterized the final phases of planetary construction. The pockmarked surfaces of the moon and planets are there to testify to it. But justifying planetary obliquities by resorting to giant impacts leaves some perplexities that deserve to be highlighted. The first arrivals, Jupiter and Saturn. Let's begin our investigation with the heavyweights of the planetary system. According to evolutionary models, Jupiter and Saturn were the quickest to form, managing to grab a lot of gas from the original nebula before the proto-sun's wind swept it away. Their evolutionary history is therefore quite different from the other planets. First, a solid core formed, then the gaseous component was acquired. Even assuming that at the end of their aggregation, the cores of Jupiter and Saturn possessed a certain obliquity induced by the most violent impacts, the massive contribution of angular momentum from the gaseous component should have subsequently erased all traces of such original obliquity. In essence, the two gas giants should possess a rotation axis substantially perpendicular to their orbital plane. But another look at our table tells us the predictions have only partly come true. While Jupiter is perfectly in line with expectations, about 3 degrees inclination, Saturn has an obliquity of about 25 degrees. Considering that the ringed planet has a mass equal to 95 Earth masses and rotates in 10.7 hours, it's natural to wonder what kind of impact could have generated such an inclination and when the event could have occurred. If it was an impact, the event must be placed in a rather narrow time window. Not too early. Gas collection would have erased the traces, but not too late either. The size of the necessary projectile would have been truly excessive. The presence of a regular satellite system around Saturn also poses further temporal constraints. The event must have occurred before such a system formed, otherwise it would have been disrupted. Resonances? A really delicate temporal choice is needed to get out of this situation. Unless, as suggested by William R. Ward and Douglas P. Hamilton in November of 2004 in Astronomical Journal, an alternative explanation is called into play. The two researchers maintain that the origin of Saturn's high inclination should be sought not in a collisional event, but rather in an orbital resonance situation. Saturn would have initially formed with a small obliquity, then been captured in a secular resonance with Neptune, and this resonant condition would have caused the increase in inclination to the current value. According to this study, it would no longer be necessary to resort to the impact mechanism for Saturn, a conclusion that relieves us, but inevitably forces us to deal with equally delicate and complicated dynamic mechanisms. All the more difficult to frame if their action is lost in the chaotic moments that characterize the final phases of planetary formation. The extreme cases of Venus and Uranus. Having filed away, so to speak, Saturn's case, it's time to dedicate ourselves to the two most problematic situations in the entire panorama of planetary obliquities. Venus with its upside-down rotation, and Uranus's strange rolling along its orbit. Let's start with Uranus, if only because a very recent study has strongly questioned the impact scenario. The idea of cosmic collision has always been the favorite explanation for the axis inclination of Uranus, an event that was also thought to explain the formation of its satellite system. According to what D.J. Stevenson proposed in the mid-1980s, it would have been an oblique impact with a massive cosmic projectile, a couple of Earth masses, that not only knocked down the rotation axis by 90 degrees, but also triggered the formation of a debris disk from which the current regular satellites would have formed. To tell the truth, the idea of attributing both Uranus's inclination and the formation of its satellite system to a single event has never been accepted with equal enthusiasm by all planetologists. To many, it seemed too fortunate a coincidence. Numerical simulations indicated that the big event could occur, but taking it for certain was quite another story. Adrian Brunini from the National University of La Plata also shares this view, author of a study that appeared in April 2006 in Nature. His simulations demonstrate that there's no need to resort to the impact hypothesis. The obliquities of giant planets would be more naturally attributed to mutual gravitational perturbations. Brunini's scenario envisions a rather fluid orbital situation, with the giant planets gradually modifying their orbits. The migration of giant planets, thanks to studies on exoplanets, is now almost established. For Uranus, the high inclination would be due to close encounters with Saturn, which occurred when Saturn and Jupiter were in orbital resonance and dominated the other giant planets. The satellite system of Uranus wouldn't be a problem. According to Brunini, these satellites would have been able to adapt to the slow evolution of the planet's equatorial plane. All solved? Not even close. Brunini himself, repeating the simulations with a different mathematical model, was no longer able to obtain the same results, and other researchers have also shown that the mechanism of gravitational interactions fails to account for the high obliquities observed. Bottom line, we're still at square one. With Venus, despite the situation being the most anomalous, inclination of almost 180 degrees, things seem better off, partly because planetologists have always been rather open-minded about it. I'm not aware of any detailed explanation of its retrograde motion resorting to a single impact being proposed. Current scenarios rather emphasize the role of its dense atmosphere, which, due to its proximity to the Sun, is subject to extraordinary effective tidal forces. If we add to this action the effects attributable to core mantle friction, we can understand how the presence of an impact isn't so necessary. It's still not clear whether what we observe is the result of Venus's rotation slowing down, stopping and restarting in the opposite direction, or the consequence of an actual flip of the planet, but it seems fairly agreed among planetologists that we're looking at the result of natural evolution. Doubts for all tastes. After having set aside Mercury from the beginning due to manifest solar interference, having observed that Jupiter is the only one to adequately meet our expectations, and having outlined some important background for Saturn, Venus, Uranus, and Neptune, it remains to define the situation of the two planets that interest us most closely. What about the obliquity problem for Mars and Earth? Their orbital position wouldn't pose any supply problem if we wanted to call in a mega impact. Around here, there was certainly no shortage of wandering rocky planetesimals during the crucial phases of planetary construction. The not at all abyssal distances separating Earth and Mars from that gigantic reservoir of unexploded projectiles, that is the asteroid belt, also reminds us of this. For our planet, the presence of the Moon provides an excellent foothold for those who intend to explain the providential inclination of Earth's axis by resorting to a violent event. The theory invoked for the Moon's formation indeed requires an oblique impact, just the type of impact best suited to inducing the rotation axis to lean to one side. For Mars, however, events took a different turn. Since Phobos and Deimos are just two asteroids captured by the planet, we have no moon to give us a foothold, but this doesn't mean planetologists start groping in the dark. Thanks to accurate numerical simulations, it's known for certain that the inclination of the Martian axis is chaotically variable, and the obliquity we observe today is destined to undergo wide fluctuations over time, up to 50 degrees. And it's not necessary to resort to impacts. Gravitational influences suffice, as already noted for Venus. Different, however, is the situation for Earth. For our planet, such a mechanism must reckon with the presence of the Moon, which acts as a formidable stabilizer of terrestrial motions. That's why Earth's axis inclination varies only 1.5 degrees in 41,000 years. It's thanks to the Moon that Earth has had the regular rhythm of seasons practically assured, a key condition for the development of life. Even for the last two remaining planets, we're therefore in a stalemate, and the conflicting answers don't allow us to untie the obliquity knot. Having reached the moment to draw conclusions, it's really difficult to draw a clear and unambiguous conclusion. On the other hand, it wasn't the possibility of finding a definitive answer that drove us to investigate planetary obliquities, but rather trying to instill some small perplexity about the mechanisms usually brought into play. Before we continue with the sun rotation, be sure to stay tuned afterwards for our earlier release on why do all the planets orbit in the same plane. And the sun? To leave the viewer with a further element for reflection, it's worth dedicating a couple of lines to the sun as well. Our star's rotation axis is inclined about 7.5 degrees with respect to the ecliptic plane, a situation that allows us, right in the first week of September, to observe its north pole, and 6 months later, obviously, the opposite pole. What to say about this unexpected inclination, given that the sun formed by contraction from the protoplanetary disk and therefore should show a rotation axis normal to that plane? In this case, it would be really out of place to invoke a collisional mechanism. Just a glance at the solar mass is enough to understand the absurdity of this hypothesis. We must therefore look elsewhere for a possible explanation, perhaps invoking the intervention of something that really had what it takes to tilt such a massive body. And why not think that this imbalance between the sun and its planetary system could have been the extreme farewell of one of those stars that formed with the sun, daughters of the same cloud of gas and dust? We don't know how reliable from a dynamic point of view such a hypothesis might be, nor are we able to evaluate in detail the quantitative and temporal constraints it requires. But we like to throw it out there anyway. Perhaps it's the fruit of incurable romanticism, but we're fascinated by the idea of a last friendly shoulder bump between sister stars before each went their own way. Why do all the planets orbit in the same plane? There are many planetary systems like ours in the universe, with planets orbiting a host star. Our planetary system is named the Solar System because our sun is named Sol, after the Latin word for sun, solus, and anything related to the sun we can call solar. As soon as they began to observe the night sky, astronomers found that Mercury, Venus, Mars, and basically all the other solar system planets orbit in almost coplanar orbits. How is that possible? An explanation for this was needed. As of today, we think the reason is the following. The orbits of the planets are coplanar because during the solar system's formation, the planets formed out of a disk of dust that surrounded the sun. Because that disk of dust was a disk, all in a plane, all of the planets formed in a plane as well. But let's see this in more detail. Ladies and gentlemen, welcome to the world of planetary formation. According to the most recent study, all exoplanets are different, and there are plenty of them out there. On some exoplanets, it rains diamonds. Some of them have an iron core. Some others have an ice core. Exoplanets may rotate clockwise or anti-clockwise. They might be rotating faster or slower, and they can be big in size or small. Some of them could be habitable with vast oceans on their surfaces. Some others, being really close to their host star, may be in a tidal destruction process that heats them up, causing strong volcanic activity. If there's one thing we understood about planets, is that they're all different from each other. But all of them have one thing in common. All planets and exoplanets were born in an environment known as a circumstellar disk around their host star. How is that possible? Let's start from the beginning. We'll use our solar system as an example. A star forms as a consequence of a dynamical collapse of a giant cloud of gas. Most likely, this huge cloud of gas was in a really unstable equilibrium state. The smallest perturbations in the gas could derive a gravitational collapse, under which the molecules become denser and denser, and the cloud shrinks as a whole. It is probable that the event that triggered the collapse was external to the cloud itself, otherwise an equilibrium between its parts. Scientists have advanced the hypothesis that it may have been the explosion of a nearby supernova, that is, a star of great mass that has reached the end of its life and explodes, expelling its entire atmosphere into space. The silent shock wave would then have given the initial thrust to the cloud. Thus, the death of a star can generate the birth of another star. The heat and energy from this collapse create pressure that, as time passes by and the cloud gets dense enough, counterbalances the effect of gravity, holding the system together. When a hydrostatic equilibrium is reached between these two forces, gravity and pressure, the star is basically born. Stars are big and hot balls of gas created by the collapse of huge clouds of initially cold gas. We think the great majority of the stars were born like this, and our sun is no exception. What really happens afterward is a bit more uncertain, but we know for sure that at this stage there's a circumstellar disk surrounding the star, and the material keeps free-falling around the star. We say around because free-falling matter does not fall in a straight line towards the center, but rotates around in even tighter spirals. The rotation of the sun and the planets around their axis, as well as the revolution of the planets and other bodies around the sun, is precisely the remnant of this initial whirlpool. At the periphery of the cloud, far from the star, the remaining material continued to rotate around the center. Then something simple, yet fantastic happened. The material settled into a thin disk under the effect of this rotation. This is a pretty basic physics concept that we are used to. Take your washing machine, for example. You fill it with dirty clothes, add the bleach, and press start. The laundry has begun. Now you observe the clothes rotating, basically orbiting around the center of the washing machine. As they rotate, they are pushed towards the walls, and this is the effect of the centrifugal force. But if you look closely, they are not pushed in random directions. They're not randomly spread out. They are rotating in some sort of a disc-shaped region. Basically, your clothes are orbiting in almost the same orbital plane. This is what billions of years ago happened to the material surrounding the sun. The material thinned into a disk as a consequence of the conservation of angular momentum, and some small bodies called planetesimals started forming as a consequence of collisions. Subsequent aggregations then led to the formation of the planets as we know them. Even today, the major bodies of the solar system revolve around our star on almost the same plane, called the ecliptic. Well done! This is the simplest and most elegant way to answer the initial question: why do planets in the solar system orbit in the same plane? But our solar system is not only made of planets. If you take a telescope, you can clearly see that other small bodies populate our planetary system. These are asteroids, frozen bodies, and dust. Scientists think that they are the oldest remnants of the solar system formation, that is, the fruit of primordial aggregations that failed to evolve into planets. Their orbits, more inclined than the ecliptic, testify precisely to the fact that these bodies were excluded from the main formation mechanism along the rotation disk. Most of this ancient space rubble can be found orbiting the Sun between Mars and Jupiter within the main asteroid belt. Asteroids range in size from Vesta, the largest at about 329 miles or 530 kilometers in diameter, to bodies that are less than 33 feet or 10 meters across. The total mass of all the asteroids combined is less than that of Earth's moon. Some asteroids go in front and behind Jupiter. These are called Trojan asteroids. Asteroids that come close to Earth are called near-Earth objects, NEOs for short. NASA keeps a close watch on NEOs because they could be potentially dangerous. Space agencies are currently looking for ways to deflect the trajectory of an asteroid in order to defend our planet. There's actually an entire field of astrophysics and engineering devoted to planetary defense. For instance, the DART mission, launched in November of 2021, will impact an asteroid on September 26, 2022, as an orbit demonstration of asteroid deflection. Basically, DART will impact the asteroid Didymos to adjust its speed and path. DART will be the first ever space mission to demonstrate asteroid deflection. We can't wait to see if it works. So we understood that as a rule of thumb, planets orbit in the same plane. But let's take a look at our solar system. Do they all really share the same plane? As Earthbound humans, we have adopted the plane in which the Earth moves around the Sun as our reference plane for the solar system. If the Sun's path is observed from the Earth's reference frame, it appears to move around the Earth in a path that is tilted with respect to the spin axis at 23.5 degrees. This path is called the ecliptic. It tells us that the Earth's spin axis is tilted with respect to the plane of the Earth's solar orbit by 23.5 degrees. With this convention, if we put ourselves on the ecliptic, the Earth has an orbital inclination of 0 degrees, and the orbital inclinations of the solar system bodies are measured relative to this. For example, Mars has an orbital inclination of 1.8 and Mercury of 7.0. As you can see in this picture, planets make nice circular orbits around the Sun. However, the dwarf planet Pluto's orbit is very different. It's highly elliptical, traveling around the Sun in a squashed circle, and Pluto's orbit is highly inclined, traveling at an angle of 17 degrees. This strange orbit gives Pluto some unusual characteristics. For example, it orbits so widely that it can switch places with Neptune, orbiting closer to the Sun. The last time this happened was on February 7, 1979. Pluto remained closer to the Sun than Neptune until February 11, 1999, and the previous time it happened was back in the 1700s. With its low mass, Pluto's orbit is actually quite chaotic through its interactions with Neptune. This means that it is not easy for astronomers to predict where Pluto will be in the next millions of years, because the uncertainties mount up and it's impossible to know where it'll be in the far future. To sum everything up, we could say that what we observe in the universe today is the result of physical processes that happened over a time scale of billions of years. On one hand, simple physical explanations can be given to understand why both the planetary systems and other objects like spiral galaxies have the form of a disk. On the other hand, though, scientists know that, unfortunately, we live in a non-deterministic universe, which is rather chaotic. This means that the slightest perturbation in a system can lead to unpredictable results. Therefore, we can have planets orbiting in highly inclined orbits like Pluto, or strange features of the fabric of a galaxy of a moon-planet system. For example, did you know that the moon is slowly drifting away from Earth? The effects of chaos, though, are only detectable over very long timescales. I mean, chaotic events keep happening all the time, but their effects are basically negligible over human life timescales. This is good for us humans because, given our short life compared to the age of the cosmos, we can treat the phenomena as quasi-static and pretend, even if just for a second, we can predict the behavior of the universe. That's all for this video. What do you think about it? Let us know in the comments below. And if you enjoyed the video, don't forget to share it, and I'll see you next time on the channel.